All right, so we had Coulomb's law that is given by this formula, and it's shown how it works in and then we have principle of superposition, which means that for total electric field of many point charges at some point in space, you find the individual electric field of individual charges at that point and then add them like vectors. So this, you get the total electric field at that point. And of course, in case of continuous charge distribution, it becomes an integral. And we did that integral for this situation, and we got to these two formulas. And then in special cases, for example, if you have a symmetrical situation, it becomes like that, but theta is the viewing angle of one end from the middle, or you can write it in terms of the length of the thin rod and the distance r from the rod. And then if the line is infinite, then it reduces to this formula, as you see. And we talked about electric field of a ring of charge, uniformly charged ring along the axis of the ring at the distance z from the center, given by this formula, kqz divided by r squared plus z squared to the power 3/2. And of course, electric field is along the axis of the ring. If the ring is positively charged, it is away from the center of the ring. If it is negatively charged, it is toward the center of the ring. And this is a special case. We said that from this formula, you see that when z is much larger than r, this equation reduces to this, which is the point charge equation, as it should be. For a disk, the electric field of a disk of uniformly charged, which is surface charge density sigma, is sigma over 2 epsilon naught times this expression. When r is much larger than z, it is like an infinite plane. It becomes like this. And for an infinite plane, we use this equation to find the electric field of an infinite plane of charge with charge density sigma. And the important thing is that this doesn't depend on the distance. It means that for an infinite plane, it doesn't matter where you are. Everywhere the electric field is the same, which is very interesting. This is for circular arc of charge q uniformly distributed over the arc, and it subtend the angle of 2 theta naught from the center. And at the center of this arc, the electric field is away from the center of the arc if center this here. If the charge is positive and is toward that point, central point, if the charge is negative. And theta naught is in radians in this formula, and it is only half of the total angle here. And then we talked about dipole, which the torque on a dipole, and electric potential energy of a dipole, and this is the dipole moment definition. And then we went through this example and this example. And then this is a question I would like to ask you here. You see, I'm always torn between these two choices. I can, ask you the questions and let you think about it and give me, your ideas, and we go through the problem. Of course, this is very good, but we go through a small number of problems, okay? But you are engaged in the process all the time. And of course, some of you are anyway. But if I do the problems myself, you listen, it is a passive activity. You're not doing anything, you're just watching, but we go to a larger number of problems. That's the advantage of this. That is the disadvantage. For this one, is advantage is that you're getting more engaged into the problem solving, but we go through this less number of problems. So I want to give you a poll to decide which one of these you like most and how much. If you like only this, you answer A or B, or say 50-50 between A and B, maybe 70% A, 30% B, and 30% A, 70% B. I want to know your opinion, and it is anonymous, so don't worry. Just give me what you think. Okay. I give you a few seconds to answer this question. You just.
Sir, will the questions on the exam be more based off the like A type of problems or the B type of problems?
It is mostly B, but it could be A too, because these are mostly conceptual. A is more conceptual. B is more problem solving, because that's hard to do multiple choice. All right, so please answer. See, I want to see the distribution. All right. Good. 85%, 86%. All right, almost everybody answered now. All right, I'm going to end it and share. All right, so you see most of you said basically you like B more than A, because either you did 70% B and 30% A, or said absolutely B, but there are some who say 50-50 or 70-30. So this is only 5 out of 47, 8 out of 47. So I guess if I do right, some time on A and more time on B, that would favor most of you. And nobody said spend all the time on A. That's a good thing. So that's definite answer. That's a very good thing. Thank you for participating in that. I just wanted to know how to divide the time between the two different cases. All right. So yeah. All right. This is the next question. It says that there are two rings, two identical circular non-conducting rings centered on the same line and with plane perpendicular to the line. Is the way it's shown. Each ring has charge that is uniformly distributed along its circumference. The rings each produce electric fields at points along the line. For three situations, the charges on ring A and B are respectively Q0 and Q0, negative Q0, negative Q0, and negative Q0, positive Q0. Rank situations according to the magnitude of the net electric field at A, point P1, B, point P2, and C, point P3. Greatest first. So this is now both of them. You see these two, situation 1, situation 2, situation 3, and we're focusing on the part A, point P1, which is at the middle of the two rings. I guess I can ask you which one of these produces more electric field in this case. So let me give you the polls in this case, and then you answer which one of these situations create more electric field at point P1. A, B, C.
What is it we're choosing for specifically?
Yeah, do you want to see which one of these situations create more electric field at point P1? A for S1, situation 1, B for situation 2, C for situation 3.
Got it.
I should have. All right. All right, I'm going to end that right now and share the result. All right, we have a variety of answers. Mostly you answered C, which is the correct answer. So, and now I'm going to explain. Does anybody who answered A or B want to explain what they thought? Because maybe I can explain a little bit better. Somebody who answered A or B, why did you answer A or B? You want to rank the situations. So I think maybe it is, they did it the other way around. All right. So in order to answer this question, again, you can find the electric field of the individual rings and see how they combine with each other. For example, here we said that this is ring A, or call it 1 or 2, or A or B. Each one of these create an electric field at this point, at point P1. Ring A creates an electric field here along the axis, and it is, because it is positively charged, it will be away from the center of the ring. See, this is the center, it will be away. So this is the electric field of A. An electric field of B is also away from its center. So these two give you 0. E net is 0 at point P1. And this one, for this one, you see each one creates an electric field that is toward its center. So for A, this one will be toward its center. So this is EA, and that is EB. And for this one, the positive, the negative one, EA, ring A creates an electric field that is toward its center because it's negatively charged. So it will be like this. This is EA. And EB creates an electric field that is away from its center. And this is the center. So away from that is here, EB. So both of these are in the same direction. Therefore, they add up to twice the length, like that. So in this case, also E net is 0. But here, E net is twice EA, or twice EB. All right. Any questions?
So you're saying that ring B is creating a force away? Is that what you're
Away
saying?
from its center, not force, electric field.
I mean, yeah, electric field. And how about, isn't the ring A doing the same thing though? If it's
In situation 3,
oh yeah,
ring A is negatively charged, so that will be toward its center.
I
Right?
see.
Yeah, EA
Okay.
is away. EA, sorry, yeah, EA is toward its center because it's negatively charged, so it becomes to the left. For EB, it is away from its center, which is still to the left at that point,
Yeah.
right? All right, so
Okay.
that is why this is the correct answer. It creates
Excellent.
a larger electric field.
Yeah,
And the
'cause-
ranking, so the ranking for point 1 is situation 3 greater than situation 2 equal to situation 1 equal to 0. Those two are 0, but this one is non-zero. All right. So what about this situation? Let me give you the poll again. This is for point P2, which is the center of the ring B. Now, what do you think? Which one do you think creates, which situation creates a larger electric field? Let's call this, sorry, call this A, call B and C. So answer A, B, C, depending on which one you think is the correct answer. Or if all the same, you can say D.
This is the same question, right?
No, the same question, but for point P2. All right, please answer more quickly. If all the same, you answer D. If not, answer which one of them. All right. I'm gonna stop it now. All right, so you see the answers are all over the place. I don't know what you think. Anybody wants to share what they did?
I choose D because point B is at the central of ring B, so the electric field at ring B is 0 and S1, S2, S3. Then Q is the plus negative. It's just same.
Okay.
So I choose number D.
Okay. Anybody else? Anybody who chose something else? I was thinking that the ring particle was on, didn't have an effective effect. So the only thing that mattered was the other ring. Okay, that's again saying D. Anybody who said A, B, or C wants to share why they did that? How they thought about it? All right. So remember that for a ring, the equation was this, the electric field equation was KQZ over square root of, or R squared plus Z squared to the power 3/2. So from this formula, you see that if Z is 0, Z was the distance from the center. If Z is 0, then this becomes 0. For for each one of these situations, for all situation, you have E for B is equal to 0 because Z for B is 0. Therefore, it depends only on A, and in A, electric field of A is away from its center at this point, means this way. Let me correct that. Means along this line, away from its center. For this case, it is toward its center. For this case, it's also toward the center, but because it's talking about its magnitude, the magnitude depends on the radius, the distance, and the charge, the magnitude of the charge. Therefore, it doesn't matter which one, each one of these have the same magnitude, but of course, different directions. So all of them are the same. So situation 1 is equal to situation 2 equal to situation 3. Okay, this is the answer. Does it make sense? Any questions?
I guess I'm confused because the last problem, it's a completely different
Yeah.
function.
Yeah, you see, because it was at this middle, it wasn't on the center of any of the disks. But from this formula, if Z is, first of all, Z is the distance from the center. For the ring B, Z is 0. When Z is 0, EB becomes 0.
Yeah.
For B.
So P here, is that supposed to be neutral?
That's a point only. Yeah, there's no charge. We're calculating electric field at a point in space. You're not calculating force. And even if you put a charge over there, the force on the charge will be EA, becomes the electric field times the charge. For example, if you put a charge, let's say capital Q here, let's say charge capital Q put here, there's a force which is equal to E net times Q. So yes, if you put a charge there, there will be a force, but it doesn't have to be a force.
Can you go back to the previous example? I want to see that. Yeah, what you had written down. Okay, so
the situation for both of them was the same.
Oh, I see. So the force is obviously reacting different, like they're negating.
Yes.
Two negative charges.
Yeah.
And then the other one, positive, they both get attracted to each other, right? The negative and the positive.
We're not talking about attraction here. We're talking about electric field that each one produces at that point.
So the positive charge is producing electric field that goes to the left.
Yes, it goes away from its center.
That goes away from its center.
Remember, for example, this one is positive. This is the center. At this point, it goes away from the center. So this is EB.
Okay.
And this is also positive. The field that this A creates is away from its center. You see that? And in this case, both of them are negative. So each one creates a field at this P1 that is toward its center. So this will be EA, this will be EB, means toward its center. And in this case, this negative creates a field that is toward its center. So this is EA. This is positive. It creates a field at P1 that is away from its center, which is EB.
Yeah, I'm not too clear, to be honest. But I guess I'll just look at the book or something like that.
No, it's just from the definition that we talked about. Just a moment. Let's go back to that. This was the situation. You see, we said that this is the formula that gives you along the axis of the ring. It gives you the magnitude of the electric field.
I see.
Right? But then we say the direction of the electric field along the axis is directly away from the center if the ring is positive, directly toward the center if Q is negative.
Hmm.
So the point is,
I didn't see this rule.
right? So
Yeah.
the this is good. No, these problems, these questions are the purpose of these questions is that you rehearse what you learn, and if you make a mistake, go back, check, see what point you didn't consider, and then that is part of learning. So don't worry about it. It's okay. It's okay to make mistakes, but that just learn. You just learn from it. Don't worry. Okay. That means that these things that we say also should be considered at each situation. Okay. So now here, we go back to the problem in here. You see, for each one, if you look at it later, you will see that we considered that fact, whichever ring is positive, the field is away from the center.
Yeah, I see what's going on now. That makes sense.
Okay.
Yeah, I got it now. I'm clear on it.
Okay.
Yeah, I didn't see the rule. I didn't know you explained it in the beginning. I kind of dropped in class a little
Yeah, that's okay, but that's why these problems are gone over to rehearse what we learned.
All right, sounds good.
So you see, at this point also, because for ring A, for ring B, all the electric fields are 0, so the net electric field is just the electric field of A.
Mhm.
And electric field of A depends on the distance, Z, Q, and radius, and all of them are the same for situation 1, 2, 3. And therefore, the net force is just EA, which is the same, therefore they have the same magnitude.
Hmm.
But the direction is different, but that doesn't, you see, it's in magnitude. For magnitude, they are the same.
And in this
Right.
case, on the left side, which is ring A, why are we not considering the electric charge from that?
Yeah, we are considering it. This is this EA is due to ring A.
Yeah, you're right. Never
The
mind.
electric field due to ring B is 0 at those points.
Oh, okay, I see. Because it's directly at the center of ring B, so
Yes.
because it's there, there's no charge being created by ring B.
No, not charge. Electric field being
The
created.
electric field. Okay.
Yeah, because Z for B is 0.
So that electric field of ring B, where would that be then? Is that kind of like vanishes? Does it go to the
0.
opposite end?
0
just
at that point.
Okay, because electric charge deals when there's two different, I guess, charged particles, maybe?
No, you see, if you put a charge here, the ring B doesn't apply any force on it because it doesn't have an electric field. But the force on that charge will be due to the other ring that's whose center is away.
Okay.
All right. Yeah, you need, it is a little bit of a thinker. You need to think
Yeah.
about it.
Yeah, because I'm seeing that it has a negative charge.
Yeah.
But the electric field is 0 simply because.
And no, the electric field of this one is not 0.
No, I'm looking at the B.
B, yes, B everywhere is 0 at point P2. Ring of B doesn't create any electric field at P2.
And that's based off of the equation, basically.
That's right. Yes.
Okay. All right. I guess I'll just consider because I see the equation. I know you can use it, like figure it out, but I guess I can't understand it.
Yeah, here, every element of charge creates an electric field here. This is negative. This will be this electric field for that. And there's another element on the other side here that creates an electric field that's exact opposite. So all the electric fields here, they cancel each other from being ring to B. You can think of it that way too.
Okay, then.
right? So yeah, you need to think about it. That's the thing. Physics
Yeah.
has some formulas, but then has some comments beside the formula, and then you need to apply it to some situation that requires thinking. Okay, where in this picture is matching with those formulas that we learned, those situations that we learned? Does it work or doesn't work? That is the thing that makes it harder. But of course, it requires practice. And if you don't practice, you don't learn it. You need to practice a lot to learn well.
Yeah. I guess I can also ask, that point P, what exactly does it represent, or what is it?
It's just a point in space. We could
Okay.
be thinking, we could be talking about any point. Now we can talk about this point P3.
Mhm.
They are the same distance from the rings, but now we want to do the same thing for this. So what do you think about that?
So P3, I mean, if we apply the rule of the ring B, which is positive charge, and we consider ring
All right.
A, which is positive.
Which direction is for situation one? Which direction is the electric field of ring A at this point P3?
So when it's positive charge, it goes away, right? So
Yeah,
it'll move to the
it's
right.
away from it. So
To the
this is
right.
EA.
And so
What about B?
for ring B, it's also going to move away, so it's going to be to the right.
Yeah. Yeah, so this is also EB. So these two add up here, right?
Of course.
What about this situation two?
They'll be both to the left side.
Yeah, this will be this EA and EB. Right? And for C?
So positive is away, and then negative would be
Oops.
towards. So that'll be canceled out. It'll be 0.
Not exactly 0 because they're not the same.
Oh yeah, you're right.
The same magnitude.
Yeah.
All right. Please don't send text because this comes in front of me. I can't see the thing. All right, so this will be EB. Oops.
Since it's away from
the center of B, EB is away from the center of B because positive, and then EA is because negative is toward the center. So in this case, they cancel partially at least because they're not the same magnitude.
So that's when we use a formula to figure out the magnitude.
Yeah, but we don't have the dimension, so we cannot use, this is just qualitative, just guessing. I mean, qualitative calculation. So this is the same add up together. And in this case, it will be smaller because they partially cancel each other. We can say partially cancel each other, not exactly because they're not the same magnitude. So we see that situation 1 is equal to situation 2, which is greater than situation 3. Right?
Makes sense.
All right. All right, so let's move on. We talked about that. So we said that each one of these quarters create an electric field like this. You see, this is let's call this E. This creates a square root of 2E because there are 2 of them adding like a square because 90 degrees between them. And these 2 cancel each other. This one creates E. These ones all cancel each other. So E is 0 here. Here we have these 2 cancel each other, but these 2 add becomes 2E. So we talked about that. So the ranking will be, this is E. It'll be E in part E greater than, greatest was that one, and then B. And then after that was A and EA and EC, and that was greater than ED, which was 0. That was the ranking here. We talked about that before. I think we talked about that too. We solved this problem. I'm going to the next one. All right, so in this case, now we're dealing with 2-point charges. The figure shows 2 charged particles on an x-axis, negative q, which is negative 3.2 times 10 to the negative 19 Coulomb at x equal to 3 meters, and q, which is 30, the same magnitude at x equal to 3 meters. What are the magnitude and direction relative to positive direction of the axis, x-axis, of the net electric field produced at point P with y equal to 4 meters? So there's no charge here, it's just a point in space. So in order to find the total electric field at point P, we find individual electric fields of the point charges. For example, this one, which is negative, creates a field that is along, remember, it's along the distant direction of the connecting the line, but it is, because it is negative, it is toward that. So this is, let's call this 1 and this 2. So this is E1, which is toward charge 1. And for 2, it is positively charged. The direction is along the line connecting them. Oops, what happened? That is the line. The direction of E1 is this, and this is another line connecting these two. And because it is positive, the direction of the electric field of Q at point P is away from the center, from the charge. So this is
same rule basically we're applying.
basically.
Okay.
Yeah, but here we're talking about point charges. Over there it was rings. For
Yeah.
each one we have certain rules.
Can we assume P to be basically like the same thing, a ring, but instead of a ring, it's just a little.
No, don't assume anything. It is, we have point charges, we have rings, we have disks, different situations. All right.
But the rule is still the same, right? If it's
Yes.
positive charge, it goes,
Usually-
if it's positive.
Yeah, positive charge is away, electric field is away, negative charge towards. Yes, generally it's like that.
We have to figure out the magnitude now.
Okay, now we need to figure out the magnitude. Yes. So you see, this is 3 centimeter. This is 3 centimeter. This is 4 centimeter. What is this R? What is this?
5.
Yes, R is square root of 4 squared plus 3 squared, which is 5. So, and you see that both of them are at the same distance R. So R is 5 centimeter here too. And then we can find, oh, meters. It says meters. So now we have the numbers, we can calculate the electric field of each one. And you know that because the same distance, the same charge magnitude, both of them have the same magnitude. So E1 magnitude equal to E2 magnitude is equal to KQ over R squared, right? So it is 9. It is 9. Let's Q here, sorry. 9 times 10 to the plus 9 times Q, which is 3.2 times 10 to the negative 19 divided by 5 squared. You can calculate that and you get a number. What would be the number? 9 over 25 times 3.2 times 10 to negative 10, or whatever that is. Becomes 1 point something times 10 to negative 10. Let's call this E. you can calculate, and if you tell me, that would be great. All right, and then, all right, we want to add these two electric fields. Now we have two electric fields, the two vectors that are in different directions. We want to add them like vectors. How do we add vectors? We need to split them into their components and then add the components. So you see that both of them have the same x component, right? Because the situation is symmetric. Both of them have the same x component and the same y component that are in opposite direction. So y components cancel out. So E net y component is 0. X components add up. So E net x is equal to 2E1x, right? So if we find E1x, then double it becomes E net x, and E net becomes the same as E net x because we don't have E net y. So let's find EX. EX is E1x. Let's say E1x is EX magnitude, E magnitude, E1, times cosine of this angle, this theta. But this angle is the same as this angle, right? This is also theta. Cosine of this angle is adjacent over hypotenuse. So E1 cosine theta, and we say E1 times 3/5, right? No, it is not 60 degrees. Don't just assume anything. We have the lengths. We can say, okay, you can find theta. Theta is tan inverse of opposite over adjacent, 4/3. This is don't text, and also please talk to me. Texting just take more time.
Right, got it.
Yeah, tan inverse of 4/3. This is about 53 degrees. But anyway, we don't need to do that because then you need to calculate cosine of theta. But cosine theta is adjacent over hypotenuse. That is 3/5. So you can say E1 times 3/5, right? And then what was E1? 9 times 3.2 divided by 25. And then multiplied by 3/5, which is 0.6. Then becomes a little bit less than 1 times 10 to negative 10. All right. Somebody give me the number for E1. Exactly 9 times 3, 27, 28.8 divided by 25.
I think I got 1.28
Yeah, 1.28
times
times
10
10 to the negative 10.
I got -20 power.
Negative 20. Is that negative 20 power? No, this is plus 9. I don't think that's right. It should be negative 10. And the unit is Newton per Coulomb. Time, oh, that was this here, sorry. Is this 1.28? No, that's less than 1.28. Yeah, maybe.
Oh no, yeah, the E1 is equal to 1.28
Yeah,
times 10 to the, I got -20 power. And then I didn't plug into the the EX. I mean the
No, it shouldn't be 10 to negative 20 power. Why is it negative 20, negative 10? I think you made a mistake here.
I don't know. That's what my calculator is giving me.
Yeah, do it again. Doesn't make sense. You can always, when you calculate something, make sure it makes sense. You see 10 to the power 9 and negative 19 becomes negative 10. So it should be around that number.
Oh yeah. That's what happened. I ignored that part.
Yeah.
Okay.
All right. So now, what is 1.28 times 0.6? Anyway, you get the number. That's not important. And the direction is so E net magnitude is the square root of, you see, EX squared plus E net X squared plus E net Y squared, but because this is 0, becomes just E net X. So whatever you found here, that would be E net. And the angle relative to positive direction, take the angle, it will be 180 degrees because it is to the negative X direction. Direction, negative X direction, 180 degrees. All right. Okay. Another question here. In figure, we have particle 1 of charge negative 5Q and particle 2 of charge Q2, which is 2Q, are fixed to an x-axis. As a multiple of distance L, at what coordinate on the axis is the net electric field of the particles 0? So we want to find the point on the x-axis where the electric field is 0. We talked about it. This is negative 5Q, and this is positive 2Q. Okay, and we said that in this situation, there is some point on the axis where the electric field is 0. Who remembers that? Remember that we said that if you consider a point in between, the charge of 2 creates a electric field that is away from itself. So this is E2, and E1 is toward itself, E1, and E1 and E2 add up. So the E is not 0 here. And no matter where you are on between, when the two charges, when two charges are opposite sign, E is not 0 in between the charges. All right. And when, again, we also said that at point here, the bigger charge is closer. So the two charges never make an equal and opposite electric field. So the point at which E net equals 0 is to the side of the smaller charge. Now we need to know exactly now where is that point exactly. We want to see where it is. It is somewhere here. It is not in this in this region. It is not in this region, so it is somewhere to the right of Q2. Okay. So let me get rid of these. So it's somewhere here. Let's call this distance x. Then at this point, E1 creates an electric field in this direction, let's say E1, and E2 creates a field in that direction, E2. And when the electric field is 0, where the E1 and E2 are in opposite direction. So whenever E1 equals to A2 in magnitude, we have 0 net electric field here. So we set E1 equal to E2 and find X.
Professor,
Yes.
one of the reasons why that the charges cancel each other out, or like the fields cancel each other out.
The fields cancel out at that point, at that particular point, only one point along the X. Yeah.
And that's because like that's also in correlation to the distance, right?
Yes.
Formula. Okay, perfect.
Yes. Because you see the charge, the closer charge is at a certain distance that is smaller. So this effect of the smallness of the charge and smallness of the distance, they cancel each other. So let's set that equation. E1 equal to E2. What is E1 magnitude in terms of the Q and the distance? At that point, at point P, E1 is K, the charge, magnitude of the charge, 5Q, because we said we always use magnitude, right? Divided by the distance of P to Q1 is X, isn't it? Squared. And E2 is what? Is K and 2Q over the distance from P.
X minus L.
Yeah, this is R2. This is R1, which is X, the same as X. Let me call this R1, means the distance of P from 1, which is X. This is R2, the distance of P from 2, which is X minus L, right? So this is X minus L squared.
Yeah.
Right?
Yep.
So now we set these two equal to each other. So K is 5K Q over X squared equal to 2K Q over X minus L squared. And you see K cancels and Q cancels. And now we get an equation that we can solve for the X. So we can cross multiply this and we get 5 times X minus L squared equal to 2 times X squared. Or you can say X minus L squared equal to 5 over 2 over 5, which is 0.4 X squared. And then we can take the root of both sides. Yes, square root of both sides. We get what?
X minus L over 0.4 times X.
Yeah, square root of 0.4 times X?
Yeah.
Not exactly. Something is missing there. What's missing? When you take square root, you have to set
Positive minus.
plus minus. If you don't do that, you may miss one of the solutions. So there is two solutions with one is positive, one is negative, one with positive, one with negative. When it's positive, this is X minus L equal to square root of 0.4. If you want, you can calculate that as a decimal times x, and then you found x. So you move x over, you can move L over, get x times 1 minus square root of 0.4 equal to L. Therefore, L x becomes L divided by 1 minus square root of 0.4, which is a positive number, right? And it is more than L because 1 minus square root of 0.4 is less than 1, right? Therefore, this should be our answer. With negative sign, if you put negative, you get x minus L equal to minus L. You get the other answer, other solution. With negative, we have x equal to L divided by 1 plus square root of 0.4. This is less than L. Less than L is in this region, which we said is not the right answer, right? So this answer is no good because it is in between the two, but this is our answer. So what is the square root of 0.4? And what is 1 over 1 minus square root of 0.4? It's a number, a certain number more than 1 times L, which becomes this distance that we want. All right. Any questions? All right. So this is how you do this. A problem like this. You first figure out which region it should be, and then you put this, you set the magnitude of the two electric fields that are in opposite direction, but the magnitudes are positive. You set them equal to each other and solve for the variable that you're looking for. Okay. Here it says two parallel non-conducting rings with their central axes along a common line. Ring 1 has uniform charge Q1 and radius R. Ring 2 has uniform charge Q2 and the same radius R. The rings are separated by distance 3R. The net electric field at point P from the ring 1, P, on the common line at distance R from the ring 1 is 0. What is the ratio Q1 over Q2? All right. So here we have the formula. We know that electric field for any ring is KQZ divided by Z squared plus R squared to the power 3/2. So this is our formula. We know what it means. Now we apply it to this problem. This ring 1 creates a they're both positive, right? Uniform charge Q1 and Q2. No, we don't know it's positive or negative. And here, let's say if it is positive, it creates a electric field E1. As Q2 is positive, it creates electric field like that, E2. And if they're the same, the magnitude, they cancel each other. The net electric field at point P on common line at distance R from ring 1 is 0. You see, the electric field is 0. We want to see what is the ratio. So we set E1 equal to E2. Right? So E1 is KQZ Q1. So instead of capital Q, I put lowercase q1 times, what is the Z for that?
R.
Z is the distance of P to the center, which is R in this case. So R divided by R squared plus R squared to the power 3/2 equal to K Q2 times, what is Z for that one?
It is, looks
Minus
like
one.
Let me
2R.
write this. Here is Z for 1. Here is Z for 2, right?
D minus R.
Yeah, D minus R, which is 3R minus R is 2R. Divide by 2R squared plus R squared to the power 3/2, right?
Explain where you got 2R from D minus R.
Yeah, D minus R, and D is 3R,
I see, thank you.
right? So Z for one of them is 2R, for the other one is just R. And you see this R cancels, the K cancels, and this R squared can be factored, and with this R squared can be factored and cancels. What we have remained is that Q1 over 2 to the power 3/2 equal to Q2 over 2Q2 over, this is 4 squared plus 1 squared, 5 to the power 3/2. Right? So we can now find Q1 over Q2 from this equation. So Q1 over Q2 is equal to 2 times 2 to the power 3/2 divided by 5 to the power 3/2. Right? Or 2 to the power 2.5 divided by 5 to the power 1.5. So we can calculate that. Yes?
I'm just curious, why is it 2R again? I didn't get that part.
Why
Yeah,
is it
2R.
2R?
Yeah, where are you getting?
The distance D is 3R.
Uh-huh.
The distance of P to the center of ring 1 is R.
Okay.
And what is the other side? That's 2R, because this is 3R.
Okay, so that's 3R, and then the distance from P1 to ring 1 is R. Oh, I see. So the remaining is 2R, obviously.
Yeah.
Okay, I see.
So here is the answer. And they are both either positive or negative. They can be positive or negative. Right? All right.
So looking at the general formula, which is Z, R.
Yeah, Z1 is R, Z2 is 2R.
Yeah, I'm like, I guess it's confusing the way they're using them. Maybe they could have used like distance 1 or distance 8.
Yeah,
plus
that's the
distance
purpose, to confuse you, make sure that you're smart enough not to get confused. That's the purpose.
Okay.
All right. It's always the same in any course. They just want to trick you to make sure that you understand the subject. All right. Let's move on. This one is similar to that, but 2 rings with 2 different radii. But we want to study the electric field of these 2 at this point P, which is distance T from the center of both of them. 2 concentric rings of radii R and R prime, which is 3R, that lie on the same plane. Point P lies on the central z-axis at distance D, 2R. So this D is 2R. R prime is 3R. From the center of the ring, the smaller ring has uniform charge distributed uniformly distributed charge Q. So this is Q positive. In terms of Q, what is the uniformly distributed charge on the larger ring if the net electric field at point P is 0? So you see that the ring of radius R, the first smaller ring, creates a field this way, positive, because it is positively charged. In order for the other one to cancel that, should create a field. Let's call this E1. Then E2 should be this way. So therefore, Q2 or Q prime should be equal to, should be negative, not should be negative. So from the situation, we see that the charge of the other one, Q prime, it should be negative. But then they should have the same magnitude of electric field at that point. So again, the formula is the same. We say E1 is equal to E2 in magnitude, but the opposite direction. Now we put the formula. For 1, we have K, Q times R times D, which is, then put D, divide by, D is 2R. If we need, we put it 2R. Divide by D squared plus R squared to the power 3/2. That's the electric field of the first one, should be equal to K, Q, D, divide by D squared plus R prime squared to the power 3/2. So see, all of these three cancels out. Sorry. This is Q prime, not Q. So that doesn't cancel. This one cancels. And D is 2R, so we can replace these D's by 2R. And D, so D is 2R. D squared is 4R squared. So we have Q over 4R squared plus R squared to the power 3/2. Yeah, we have Q prime divided by 4R squared plus R prime, which is, R prime is 3R. So R prime squared is 9R squared. So 9R squared to the power 3/2. So we can say Q prime over Q, we can calculate, will be, this goes up here, and this one is in the denominator. So it becomes, and R squared can be factored and canceled. So R squared cancels from this equation. What you have here is 13 to the power 3/2. So 13 to the power 3/2 divided by, here we have 5 to the power 3/2. So 13 over 5 becomes 2.6. So 2.6 to the power 3/2 or 1.5. Okay. So this is a number, we can calculate that, but Q prime Q prime is negative of that magnitude. So Q prime equal to that number. What is 1.6 to the power of 1.5? It's, or it's, I think 4.2, I remember, about 4.19, or yeah, 4.19. 4.19 Q, but because we know it should be negative, we put negative. So make that more properly, negative 4.19 Q. Negative comes from the situation, not from the math. Okay, we know that it should be negatively charged because in this equation, actually, there is an absolute value here. We usually don't talk about it, but it should be absolute value. So we put the positive value, and then at the end, we know it should be negative. So we put a negative sign. All right.
Professor,
Yes.
can you go back to the previous problem, the work you did? I kind of just want to see that. Oh, okay, I see.
I will put those slides on Canvas later on.
Okay, yeah, no, I just want to compare this one to the one you just did right now. How do you say
Yeah.
it?
Yeah, in this case, you see radii were the same, but the distance to the center, which was Z, was different. Here, the distance was the same. The radii are different.
Yeah. Okay, all right. Well, you post the videos, right? I don't know if you're posting this lecture now on YouTube.
Yeah, these slides I put on Canvas after.
Okay. How about the recording, the
Recording I put on YouTube. I don't have room on
Makes sense.
Canvas. All right.
Right.
Time is over. We have a couple of more questions to go through. Yeah, we continue that next time. All right, any questions?
So on our next lecture, we will go over the problems.
Yes. Yeah, similar to this. We go over several problems next time. I have 2, 3, 4, 5.
Okay.
I may put a couple more.
So we're gonna stick to doing problems now, right? Because I already read the book and I feel like I'm basically,
Yeah,
like
reading the book.
gonna...
Reading the book is very good. You should do that. That is not enough. The way you learn physics is to do problems.
Yeah, okay.
Yeah, and even watching me doing it is not good enough. You have to do more than that. Yeah, go. Yeah, you can go through some other problems that are not here and try to do them.
Okay.
Of course, we have office hours. You make sure, if you solve a problem and you have difficulty doing them, you come and ask me during my office hours. Let me see, I wanted to stop the recording.